Hi, and welcome back. This is devlog number 12, and today I'm just going to do a bit of a run through of some code that I've written the last week. I've created an engine class and a rendering class, and done a bit of tidying up in the log class. So this is where we're at. The idea is that we have this client, gameapp.cpp, which feeds all the game logic to the engine, including what maps and assets to load. That would then send run the game loop, which is the central part of any game. And this game engine will have compositions of all these other systems, such as audio, the renderer, which we've chosen as Vulkan API, which I've had a bit of a look at. And we'll do a Vulkan Hello World screen shortly. Entity component system, which has a whole bunch of other systems, and part of that is collision detection. And all the events such as mouse movements, keyboard, joystick, gamepad, so on. And the game engine will sort of wrangle all these resources, so that's sort of the central place. I want there to be good flow in this game engine. I want to be able to look at this code in 6 months, year, 2 years time, and be able to understand very quickly how the code flows. So I'm just trying to sort of pick an architecture that is kind of central and doesn't have a lot of twists and turns. It should be quite readable. I think that's very important. I think the more experienced you are at coding, the more important it is to make your code not tricky, just as simple and dumb as possible. That means probably not even having the most efficient code. There's no point having efficient code if it's full of bugs that are just absolutely impossible to track down unless you have to rewrite whole chunks. And there's always opportunity in the future to tighten it up to make sure that everything runs as efficiently as possible or to an acceptable level. In any case, as with any technology, you're always creating a set of compromises. Like when you buy a video camera, you know, do you go for high pixels? Do you go for image quality? Do you go for the lenses that come with it? The manufacturers have to decide what the battery life is going to be. No point having a powerful processor if you can only get 20 minutes out of your video camera or your photography camera. So a lot of compromises have to be made, and this is no different for a game engine. So this is going to be like either a first-person shooter, maybe a third-person type of game engine. I want it to be lean, I want it to be fast, and it's going to lean very heavily on the Vulkan API. So that's enough talking there. Let's get into it. So before I get into the actual engine class and the renderer class, I've done a bit of fixing of this log library that we created. So now the shared pointer is in the header file. I found out, because I created a destructor, I found out that the destructor was being called every single time a get instance was called. So it wasn't working. So by moving this shared pointer, it's the only shared pointer in the program so far, not a huge fan of pointers. They can run into a lot of issues down the track and can make your code a little bit complex. I mean, I think we will definitely have pointers in this game engine, but you don't want to create them for no reason. But this is a singleton, and there's a good reason to have it, especially a shared pointer. It does all the reference counting, and there's no tidying up. It just, when the program's finished with it, it's removed automatically. So there's no chance of things going wrong in that regard. Touch wood. I've also beefed up all these, added all these methods. So now it will write various types of integers. Probably say you could probably make that as a template. This works. I'm not actually sure how to do a template just for methods within I haven't tried it yet, within actual class, without ruining the whole class, making the whole class templated. So this will probably do for now. And the code for that's quite simple. It's just converting the number to a string and sending it to the right. And returning this means that it's chainable. I've also moved the enumerations into the class. They used to sit outside the class, but this makes things a lot simpler now. So For example, when you're setting color, it's just log colon colon yellow. It's not a whole big long string. So that's a lot simpler. Okay, I've added a few more things. Yep, so I can get rid of this. Moved into class, we did that. Let's go down the list. So I added these. Oh, that's right. So now it can log to a file name. So this might be important when I don't want it logging to the console. Maybe I want it to log to the console, but later on I analyze all the logging data that I've been collecting, especially when I'm debugging. There's no point doing it in production, really. There might be some utility in that, but... And so set file name. Basically opens up a file stream and sets this Boolean flag. And you can see I've added file name and file stream. Probably don't need to have file name there, but it'll do for now. To the private section of the class. The private section of the class means that nothing outside of the class can actually handle it. So you can't actually have an object that will handle this file stream, for example, directly. It has to go through the interface, which is everything in the public section. So we can enable the console, we can disable the console. I'll just show you what it looks like when I run this program. So it creates a log file on the drive, prints out some pretty graphics. But we can disable it, sending the text to the console. We can also disable it, sending it to the file. We can have it sent to nothing if we wanted to. So the constructor's here now. Can't remember what's in the constructor. Sorry, destructor. That's right. Just for my own sanity, it just says that the destructor's been called. Like I said before, it was actually being called multiple times, and so I had to move that static get instance thing to the header file rather than having it in the CPP source file. So I can show you that. There it is, it's been called right there. And it's telling it's closing the file. Okay, what else have we got in the log file? Oh, we added a timestamp. This basically grabs the year, month, and the day. It doesn't grab the time information. I might put that in the future. You see at the top there? And this is how I call it, just time, date timestamp. And it's chainable. Everything's chainable. And that's about that. So I created a timer function. So I'd rather not do this sort of offline programming. I'd rather show you the process and hopefully try and explain the thought process behind decisions that are being made. Trying to get better at that, but I've been pretty hit for time lately, so I've had to create these things offline. So this timer scope's interesting. I can give an example. Probably the best way to show it. Oh, here we go. So this is actually the variable name that it sets up. There's a bit of text to go along with it. When it falls out of scope, I'll just show you. Let's say put it here. It'll just send a message back to the logging class to say the amount of time that's lapsed. So this timer scope is only active for the scope that it's in, so you could do profiling of any of your functions or methods just to see. You put it at the beginning of the method, and when it gets to the end of it, or a block, or any kind of scope really, but yeah, when it gets to the end of the method or the function, it'll just send the amount of lapse time to the console. So I'll just show you how this works. So start to end timer. There it is. 2.8 seconds or milliseconds, which is 1/1000th of a second. Just to give you an idea what a millisecond is, 16.6 reoccurring milliseconds is the amount of time that you have to render something to have 60 frames per second or 60 hertz on your monitor. If you want to do 120 frames per second, then it's half that. So it's, what's that, about 8 point whatever milliseconds. So it just shows you how little time you have to render each frame. So yeah, we can stick this absolutely anywhere. We can have multiple ones if you want. So in the constructor, we can give it a name. Let it know that it hasn't stopped yet. We call start. It says the start method, stop method. So the start just sets this time start point, which you see in the private section here. Here's using steady clock, so this is the actual type. Using the chrono include file. So there's the start point, there's a name, the start point, and a flag to say whether it's stopped or not. So it sets that start point, and when the stop gets called, and then look, it records the time right now, puts in this variable, converts it to a number that's useful. It's actually a 64-bit unsigned integer, which is hilarious, but they can be very large numbers because we're talking about microseconds, which is 1/1000th of a millisecond, which is 1/1000th of a second. And I mean, this actual class can go on for a very long period of time. So that's why we've got 64 bit integers. And you just take the end from the start, sorry, the start from the end, convert it into microseconds, milliseconds, print it out. I also return the value in case I want to use it. So the way this, you can actually force the timer to stop if you wanted to. So let's look at the destructor. I said if it's not already stopped, stop it. That's when it prints it to the screen. When we're creating an instance of this class, it will just call the destructor when it gets out of scope, and that's when it returns all this information. Let's get to the engine class now. So this engine class is called by, I'll create an instance of it in the client. So go back to this diagram. Here's the client. Creates an instance. In here we'll have the loading maps, business logic, game logic, all the assets that are required, how it wants to present it, beautiful music, and then it will execute the game loop. So the engine's pretty much the heart of the engine. And we have a method to initialize, which is called by the constructor, so we don't have to call it. It's already done. We deinitialize everything, free up all the resources. This is automatically called at the end of the game loop. So once again, we don't have to call that. And here's the game loop, which we'll get into in a minute. And there's various types of data that we're recording. So we have frame numbers. Frame number starts at 0, just keeps going up. When it gets to the end of the range of the frame number, it just cycles back to 0, hopefully automatically. Haven't actually tested that. Maybe I'll set an upper limit and just cycle back to 0 when it hits that number. So when we get into the entity component system, it might be useful foreseeing down the track that if we've got assets that or entities that have components that need to be updated, it'll be good to know, keep a track record of what frame number it's on, just so it doesn't get dealt with twice. It also might be good for debugging as well. So I think frame number would actually, and probably for if I do multiplayer stuff, it would be useful to have that synchronized with like a central server, so everyone's on the same frame number when it comes to the timing of various events. There's just a lot of reasons why it's probably good to keep track of what frame you're on. A frame is just an image put on the screen. It's not like 20 frames per second or 60 frames per second. It's just whatever your graphics card can handle. But I'm just thinking now that if we get into multiplayer stuff, which I don't know if I'm going to do, then it might be useful to actually have a separate one for that. Like a tick rate or something. There's a time point. So at a certain point in every game loop, it will just record what the current time is. And the difference from the previous time will be delta time, or change in time. And that's recorded milliseconds, or 1/1000th of a second. So it's pretty sort of bog standard stuff, I think, for a game engine, the bit of research that I've done. So this is the constructor. It sets the frame number to 0, prints some pretty stuff on the screen. Destructor doesn't do anything yet. But the constructor calls the initialization, which is this next one. This is what I talk about flow. You should be able to read the code, and it should logically lead from one section to another, so you can pretty much create a list of the order in which things are created and destroyed and set up. So it shouldn't be you're not jumping all over the place between different files to do stuff. For example, the whole timer thing, I could have put into another class, just a timer class for this engine. I might still do that in the future, but I'm trying to keep as much inside the engine class as possible. So you're not having to jump around trying to figure out how does this thing work. You come back in 6 months' time, you go, what is this? I don't know what this is, or how it actually all glued together. So yeah, that's why I think it's important to keep these things simple. So it sets the timer, gets it going. Renderer init. So if we go back to our diagram, so we've got the engine there, and these are all components. So the renderer, the entity component system, collision detection, the events, all the mouse, keyboard stuff, audio, including any of the resources, everything is a component. So one of these components is the renderer, or the Vulkan API. And at this stage, I want to keep it as clean as possible. By that I mean, I don't actually want to have API calls of Vulkan inside my engine. And the same when I get into audio. I don't know what audio library I'm going to use, but I want it to be a interface. So there's a layer of abstraction, if you like. So I can swap out whatever graphics or sound engine that I have plugged into the system, and it should pretty much be very close to the same sort of interface. So swapping things in and out should be quite straightforward, and means you're not binding all this code to the engine. You're just treating these components as their own little black boxes. So this is why I've created the rendering class, which we'll get into in a bit. It has might as well do it now. It has initialization, which calls create window, checks for extensions. That's what we're doing at the moment. Here's a create window. This is very straightforward, boilerplate Vulkan sort of code. And you can go to the Vulkan website and you can see everything that's sort of example hello world type of applications. We're not going heavy into Vulkan for this video. I'm just trying to set up the framework. Okay, so let's go back to our engine. Yeah. So initialize the renderer. Here we'll put in all the other stuff that we need to initialize. Geometry, sound card, the sound library, whatever. So that's called automatically by the constructor. So the constructor calls initialization, which then goes to the renderer, initializes that, initialize anything else, sets the time point. Now, if we go back to the client, for the instance of this class, the engine class, we run the game loop. And this is the heart of everything. So it's all contained within this while loop. So I have a flag to say keep running true. If this turns to false at any point, this while loop will just come to an end. The other way it can come to an end is using a library called GLFW, which we'll get to in a minute when we get into the Vulkan stuff. At the moment, just seeing whether the close button is clicked on the, I can just show you. Click the close button, and then it'll exit this loop, continue. At the moment, I'm just capturing every 60,000th, 654 thousandths of a frame, and printing the time from the previous frame. So I can show you that. There it is. So 0.001 milliseconds between it. There's not much happening at the moment, so it's spinning through quite fast. GLFW poll events, that's checking for keyboard, mouse, all that kind of stuff, I think. Or in this case, it's we're just seeing whether the window should be closed or not. And then it exits the gaming loop. Sends a message to the console saying it's exited the gaming loop. Automatically calls the deinitialization. So this client class only has to run, once all the maps and stuff and logic has been loaded up, it just has to run the loop and then it exits. That's it. The engine takes care of all the tidying up. So it runs additional deinitialization. In this case, I have to destroy the window. So that's actually in the Vulkan code. So I should eventually, I think I probably should move the gaming loop, any Vulkan stuff in the gaming loop or GLFW. So this should probably go in the, I probably need to move this into the Vulkan class, rendering class, or I might even create a separate class, I'm not sure at this point. So I want to keep any API stuff out of the game loop, out of the engine, so it's all abstracted. Like I said, so we can just swap different libraries in and out if we move to a different library, or even write our own windowing classes. Then we want to be able to do that without sort of having all this stuff sprinkled all over your engine code. So that's the clean way to do that. But we're just prototyping at this stage, so I think it's fine. But I just want to keep that in mind. So pretty soon, I think I'll probably move that either into the Vulkan rendering class or into another one. Same for this polling of events. And I'll just show you the Vulkan class now. Actually, we'll make sure we've got to the end of it. So it deinitializes, yep. Yeah, it just unloads all the resources, so. So Vulkan has initialization. Let's find that. So the constructor automatically sets the width and the height. We'll probably have something about having a full screen thing in there at some point. Here's the initialization. So rather than having the problem with Vulkan is it's a very verbose API. You can get thousands of lines of code before you even put a triangle on the screen. We're at the very beginning part of that journey, and the research I've done, so I just want to break up any things. Rather than having like 1,000 lines of code here, I'm just going to create them into little sensible blocks of these little methods. So the first one is creating a window. So this creates that white box that we had earlier with Hello World at the top. And I still need to research these. I think you can select which monitor you want to send it to, and sharing, I'm not sure what that is, but we'll probably get into that at some point. These flags here, because Vulkan comes from a lineage of OpenGL, that's its predecessor. So there's a lot of sort of old OpenGL DNA in the Vulkan API. And what we're basically doing with this flag is to say, this is not an OpenGL application, it's a Vulkan application. So we've got this bit of silly boilerplate stuff going on here. Window hint. Okay, so let's create window. The next thing is to check for extensions. And that's as far as I got so far. So more boilerplate code. This bit here essentially counts the number of extensions. I think I can put a structure in here which will pull out all the information, which we'll probably do next. But for now, let's run this. Stop it. So we've got 20 extensions. If that number was 0, then we'll be in a lot of trouble. So Vulkan is very similar to OpenGL in the sense that there are a lot of features that you can check to see whether they're turned on or off, so that you can determine what sort of technology you're going to use to run your game engine at runtime. It's different to something like DirectX, like DirectX 11, DirectX 12. That's basically my understanding, and I haven't done DirectX for a very long time. I can't remember last time I used it, dabbled with it. Is they have a set amount of features. So if it's a DirectX card, it's expected to have all these things. So it's a lot simpler in that way. But looks like Vulkan have gone down the route of having the option for graphics cards and their drivers to have a certain number of extensions. The card in this computer is a bit old. It's a RTX 3060 Ti, so it doesn't have anywhere near all the extensions that are available. I think I'm using Vulkan 1.4 point something or other, so it doesn't have them all. But it's not a 5090, for example. So why would it have all the greatest and latest stuff? So that's where we're at with that. I'll just show you the libraries that I've installed for this to work. So Vulkan, I'll just put up a link on the screen now. This is the website. You download the SDK and you install it on your system. And I've just moved it to a third-party directory and put it in another directory called Vulkan. So here it's loading Vulkan/vulkan.h is the header file. That's all we need. This is future me. I've also had to, in my pre-make file, which then gets converted into Visual Studio project files, added some include directories to these third-party libraries, as well as any libraries, such as the Vulkan library. You can see the GLFW library. For both the engine and exactly the same for the app, although the app now links to the static library Axle engine. Okay, thanks. GLFW, should be W. That's just an easy way of creating windows, drawing context, mouse and keyboard interaction, so that you can have Vulkan running on various different operating systems, platforms. Takes care of all that boilerplate code that you need to write. I think in OpenGL it might have been Glut, might have been the equivalent, I can't remember, but this will make a life a lot easier, and I can't see any reason to move away from that at this point and just do the sort of old Win32 way of doing things. You know, right? I just don't want to handle all that. So that's a pretty good library. GLM, I know I've written, there's a math library, and it's just a header file, which you can see I've put here. So GLFW, I've copied into there. GLM, I've copied into there. So that has a math library. I haven't really had a look at it yet. So I'll be using a bit of that because I'm going through various tutorials online. But at some point I'll probably move back to my own library. I want to use SIMD extensions to create very efficient Windows only code for, say, matrix manipulation. So you can use the extensions on your Intel or AMD CPU to make a lot of these repetitive matrix type of operations a lot faster. So it's not an area I've actually gone into before, but I know that exists, so I hope to be able to create something that competes against this. But a lot of tutorials use this, so I'm going to use that for now. So this define just forces us to work in radians. So a radian is basically 180 degrees is pi, so I think 360 degrees is 2 pi, so it's 6.2 whatever, 28. And that's what a lot of mathematics is done in radians rather than degrees, which is 360. I think I probably find degrees more useful to be working with, but this is sort of the pure mathematical way of doing things, I guess. And GLM force depth 0 to 1. So in my research, I found that Vulkan will set the depth between -1 and 0, but we just want it between, that's a range of 2. So let's just have it between 0 and 1. That seems to be the sort of standard practice. I think this relates to like the Z depth. So if you're looking at the screen, you might have the near clip plane and the far clip plane. It might have to have something to do with depth of field if you're going to add fog to the scene. You pretty much want everything between 0 and 1, whether it's a color range or whether in this case it's a depth range, or even the width or the height of the screen. You want everything 0 to 1, 0 to 1, 0 to 1, all directions. So we'll find out what that's all about, but that seems to be the standard practice. So let's take that for granted for now. And that's the thing with this sort of software development. You don't have to know everything at once. You just try it and see how it works, and you beauty, just go on to the next thing. And then later, dig down, get into the weeds and find out what's really going on. Those are the 3 libraries: Vulkan, GLFW, and the math one, GLM. So yeah, we create a window, which is there. Check for extensions there. So I think in the next video we'll look at drawing a triangle on the screen, and then after that we'll be loading in 3D geometry and resizing the screen, doing all the things that you expect an application to do. Move around that 3D geometry, and then we'll get onto things like collision detection, ECS, entity component system, all the various systems that are required for a game engine to actually function. And along the way we'll learn about shaders and all the things that make your program look nice and pretty, and then of course sound. So we're just building it up component at a time. And any questions, just drop down to the comments box. I want to do most of my videos actual coding live. This is more of a code review, I guess, but we're in a very boilerplate part of writing this game engine, where you're pretty much just cutting and pasting sample code from the Vulkan website and whatnot, various tutorials. It's kind of the ugly phase and boring phase for me of this whole process, so I probably will for the next few videos just show you what I've done. And as we get back into the more gamey side of the game engine, ECS, entity component system, that we'll just write that from scratch like we have in the past, and I think that'll be a bit more of a learning process for you and me. Yeah, until next time, thanks, bye.